Hello, welcome. This is the AQA A2 Physics topic video. This is all about gravitational fields, okay? I'm not going to go into electric fields, obviously, in this video, because weirdly enough it's called gravitational. But as I said, that is just kind of the next few videos. Now this is the, I don't know why I'm saying this, but why not? This is the second take of the gravitational video. The first one kind of made a bit of a mess up of it, but anyway, don't really need to say that, but I have done. Okay, so what do we mean? Ignore the kind of stuff on the board behind me, even though it's like, I'll write it on there before the video, but do ignore it. Anyway, so the most, well, Newton's second law says, I'll explain why I'm stating this, F equals ma, so the resultant force is equal to the mass times the acceleration. But if you're dropping something in free fall, okay, no matter what object that is, the acceleration will be equal to the acceleration due to gravity, g. And in this video, we're going to, I'm going to show you how we calculate g to be approximately 9.81. I'm going to prove that's the case later on in this video by derivation of Newton's second law. Okay. Okay. So anyway, if A equals g, then we can say the resultant force for an object in free fall is equal to mass times the acceleration due to gravity. In other words, F equals mg, which you can rearrange to get the acceleration due to gravity is the force gravitational over mass. Okay, so that's all we can do so far at the moment. But one of the first things I want to introduce you to is this idea of uniform and radial fields. Basically, radial fields is many of these field lines, because obviously it's the essentially gravitational attraction is attraction of a smaller mass to a large mass, or a small body to a large body. They mean the same thing, okay? Alright, so these field lines here are just going straight into the centre of the Earth, because that's obviously what it's all attracted to. This uniform field is just, it's basically, the radial field is the uniform field, but it's spread out over a greater distance, if you can think of it like that. But really, this definition for uniform field is wherever you are in the field, it will have the same direction and magnitude in terms of the gravitational field strength in, obviously, which direction it's acting in. Okay, so that's uniform and radial fields done. And I've just given a bit of an introduction. We're going to be using this, as I said, we're going to be going off that formula a bit later on, as I said, to establish what G is. Okay, so hopefully that's made some things. Right, now this isn't, I've given you that's a brief, very brief overview of what gravitational fields look like surrounding Earth. But we also have these, what they look like is sort of extended circles around Earth, okay, which cut through these field lines here, you know, radial field lines. And basically what they are is we call them something called, a very fancy name, equipotentials. And basically all that means is it's lines of constant gravitational attraction, because if you're a certain distance away from Earth, okay, doesn't matter what position on the circumference of, you know, say this equipotential is say 300 miles away from Earth, something. I mean, that sounds big, but in relative to how far away from Earth, that's nothing, okay, relative to space and time. But as I said, we won't get into that. So it's 300 miles away from Earth, and wherever you are, wherever you are, that is 300 miles away from Earth, it will have the same value of gravitational attraction, because you're the same distance away from the core, because obviously the core in itself is circular, so it's obviously, the radial field will be circular around it, okay? So if you're 300 metres around it, but it doesn't matter whereabouts on the circumference you are, you'll be the same distance away from the core, because obviously the core is circular as well. Does that make sense? I'm going to say, does that make sense? And someone's going to go through the camera. The camera's just going to speak. Yes, well, it does. Very good. Well, thanks. Anyway, right. So hopefully that makes sense. Basically, equipotentials is lines of constant gravitational potential. And obviously, as you get further away, these values become less and less. But you can almost think of it like when we did the ground state of an atom. It looked very similar. We've got these circle things with. And I know they were energy states when we were looking at a very small atom, but you see how physics takes something really small and applies it to something quite big. Anyway, before I can bind you up some more. Alright, so that's equipotentials. Now, we have something called gravitational potential. Now, this is one of the things in physics that's quite annoying, because in AS you obviously learn something about, hopefully, gravitational potential energy, which is known as GPE. Well, we're going to be looking at gravitational potential, and they're two totally different formulas. Gravitational potential energy is, well, we're looking at, the reason why this is different to gravitational potential is, in gravitational potential we're looking at the distance away from Earth, whereas in gravitational potential energy we're on the surface of Earth, so G doesn't change, and I'll just explain why. Alright, so it was mg times delta H, whereas gravitational potential energy is something quite different. As I said, gravitational potential energy is where we're considering we're on the surface of Earth. And obviously, anywhere on the surface of Earth, the gravitational field strength is 9.81 because we're at the surface of Earth. So the distance to the core, which is obviously half of the diameter, is the radius, okay? So the GPA is the same. As I said, that's like, if you're on the surface of Earth, it's like being on one of these equipotentials, but you're at the equipotential which is on the surface of Earth, okay? So that's why it's the same all over the surface of Earth. But as I said, we won't get too much into that just yet. Anyway, so that's gravitational potential energy, just a bit of a refresh, and that's why we can assume G, this is that constant. Alright, so gravitational potential energy was defined as the work done per unit mass. In other words, gravitational potential, I'm going to label it as V, is equal to the work done over the mass. Okay, so that's the formula. But we know that the work done is force times distance. Okay, so you can label it as the gravitational potential is force times distance over the mass. But to get force times distance, well, what's the force and what's the distance? Well, the distance could be between these two equipotentials, okay, which we'll call delta R. Right? And the reasons of force there, well, obviously gravity's trying to pull you into Earth and make you die and crush you and kill you. But apart from that, it's trying to get you to the centre of Earth. Okay. Right. Okay. So therefore, we have to overcome this force. In other words, the force that we have to put in to get ourselves away from this is in an opposite direction to the force that gravity is acting in. Okay, so that's why we have where the work done is negative F times delta R, and obviously that's over the mass. Alright, now you can obviously rearrange that to get the work done is equal to the change in gravitational potential times by the mass, by just simply rearranging that formula or that formula. Same to mean the same thing. Okay, right, so hopefully that makes sense. So you could rearrange this to get the force, if you wanted to. So the force would be equal to m times delta V over R. Now, as I said, the negative there only shows how it represents an attractive force, which is something involved in Newton's second law. Newton's law of gravitation, which we'll go on to in a minute. Okay, so all that negative shows is that it's an attractive force. We get a similar thing when we go on to look at electric fields later on in the course. Okay, right. So what I'm going to show you now is we go on to this statement that we're going to build up to, and I'm going to prove that the gravitational the gravitational field strength, or G, is equal to the negative of the potential gradient. Potential gradient. Now, let's understand that. But what is the potential gradient? Okay. Well, the potential. So that's gravitational potential. But what's the potential gradient? Okay. Now, potential gradient is basically. Well, there's no other way to really put it in terms of, it's not actually termed such as a statement that we can get, apart from the fact we can say that there's a change in potential over a small distance r. Okay, so the the potential gradient, okay, equals delta V, change in gravitational potential, and the change in distance, little r. Okay. Alright, hopefully, as I said, that makes some kind of sense. Now, what we're going to do is combine this formula over here, which is G equals F over M, or F equals mg, with this equation here, because they both state about the gravitational force, okay? And we're going to combine them to show that the gravitational potential is the negative of the potential gradient, okay? And the potential gradient being delta V over delta R, okay? So it's just one of the statements that you kind of need to get to grips with. Okay, so the first thing that we need to do is obviously make F equals mg equal to m times delta V over R. Is that right? Sorry, 1 second, let me check the time. Yep. Well, technically it's delta R, but doesn't matter. Okay, because F equals mg and F equals m times delta V over delta R, they both equal force, okay? We're talking about the gravitational force here. We can make mg equal to m times delta V over R, okay? Now, what we can do here is because we're both considering the same mass, we can cancel out the masses. In other words, we divide both equations by m, by the mass, okay? So that obviously gives us g to be equal to, sorry, that F equals negative, by the way, and it's negative delta V over delta R, okay? So basically, so what we've done here is make F equal mg and F equals m times delta V over delta R. We combine them together, divide both equations by m, okay? And then we've got g, the gravitational field strength, so it would be delta V over delta R, which is quite clearly, you can see the negative of the potential gradient, okay? So really it's just kind of using an equation that we know with an equation that we've just been given, okay? So as I said, hopefully it's starting to make a bit of sense for you. Alright, okay, so that's the first little bit that you need to be able to understand. Okay, what you need to do actually is, so what I'm going to do is rub all this up in terms of put a few key bits on so we can move on to the next thing that we want to talk about, which is Newton's law of gravitation, okay? Now I'll build up to that, right? So just give you a second if you want to copy that down, and we're going to move on to the next little bit. So, anyways, we're saying we're going to look at Newton's law of gravitation. So we've looked at his 3 laws of motion, okay? So his first one, we're stating about if a body is in equilibrium, okay? If all the forces acting on the body are equal and opposite in terms of, if it's being pulled forward by the same force, by the same amount of a force that's pulling it back, it will either, if it's at rest, it will remain at rest, or if it's at speed, it will remain at that speed. In essence, it will remain in equilibrium. And then obviously our second law was F equals ma, and his third one is for every action there's an equal opposite reaction. You can think of that as pushing a wardrobe. Anyway, he also looked at this gravitation. Okay, so it actually goes on quite a little bit from F equals mg. Okay, it does go on from that, but not strictly from that. Okay, there's a couple of statements that we build up to get this law. Okay, the first statement is that it's always an attractive force. Okay, so a larger force is attractive. It's never repulsive. Okay, in other words, always. Well, I guess that says quite self-explanatory. Always an attractive force. Okay. The next 2 points are more kind of building up the actual formula. That was just a kind of a why we always basically the force is equal to negative of an answer. That's what the first point says. Okay. The second point says the force is directly proportional to the sum of the masses. When I say sum of the masses, it's not mass 1 plus mass 2. It's mass 1 times mass 2, proportional to the sum of the masses. Okay. The third point, it's inversely proportional the force is inversely proportional to the square the distance. Sorry. Now, obviously, I said the first one was F is equal to a negative of whatever these 2 points give the formula to be. Okay, so the first one really doesn't tell us that much about building up the formula. The second one does. The force is directly proportional to the sum of the masses. So if we write that in terms of how we normally write this up, F is directly, fish sign, proportional to the sum of the masses m1 times m2, we'll call it. So therefore, F is equal, if it's directly proportional, it's K times m1, m2. Okay, but you also have to take, so that's what we've got so far. And obviously it's negative K m1, m2 if we apply the first rule as well. This third point says the force is inversely proportional to the square of the distance, okay? So therefore the force is inversely proportional to the square of the distance. Okay, in other words, F is equal to F is equal to K over R squared, or F is equal to K times 1 over R squared, in other words. Okay, so hopefully, as I said, that makes some kind of sense. So if we put all of this information together, okay, what we're left with is F equals negative K m1 m2, but because it's also inversely proportional to the square of the separation, or the distance between them, we have to divide it by R squared. Okay, but what is this K? That's pretty much the formula, but we just need to know what K is. Well, as we're talking about, weirdly enough, the gravitational side of things, the universe, this constant is called the gravitational constant. It's just a constant of proportionality. It's called the gravitational constant, which if you look in your formula books is 6.67 times 10 to the minus 11 Newton meter squared per kilogram. Okay, but as I said, gravitational constant. You're given that in your formula sheet, so you don't need to know that anyways. It's absolutely fine. Okay, so this is your gravitational constant, which we label as big G. Okay, so that's not one of your, one of your friends. Okay, so it's your gravitational constant. That's your force which relates that. Okay, so that's Newton's law of gravitation. Now, what we can do, and this is where it gets a bit interesting. Okay, so that's the formula. What I'm just going to do now is quickly rub all that out. Okay, but I'm going to put the formula back. So then 3 points kind of just help you to build it up. You don't need to know how it's built up necessarily, but it's always nice to know. So anyway, I said the force, the gravitational attraction force is negative G m1 m2 over R squared. Now, just the negative, obviously you say, oh, we'll never have a negative force. Well, that just shows it's an attractive, so really it's just gm1 m2 over R squared, which said that first point says it's an attractive force. It's kind of irrelevant. We already know that. We don't need a point on the formula to tell us that. Anyway, so that's the force. Now, if we want to work out, say, obviously want to work out the gravitational field strength of Earth, because I was saying, I'm going to prove to you in this video that G is equal to 9.81. And obviously, well, it's not going to come out directly to be that, partly because I'm going to use some rounding errors, okay? Obviously, there's some errors in the calculation of it anyway, and I'm going to be increasing that amount of error by rounding the number. Anyway, I'll explain. Just going to get us a formula sheet in here, which should have certain things that we want. Anyway, so well, I'm just trying to find this. So we know that the force, gravitational attraction force, that's what these both say. The one on the left says it's mass times the gravitational field strength, and the one on the left, and the one on the right of that is obviously what we've just worked out. Okay, so what we can do is we can divide both sides, or in other words, F equals mg, we rearrange out to get the g, which is the gravitational field strength. So we divide both sides of the equation by m. Okay, so therefore the gravitational field strength is the force, gravitational force. There is. Over mass, so G is equal to F over M. and we'll call that M2. And if we apply the same principle here, so we can work out this is the gravitational field strength, G is equal to G M1 M2 over big R squared, okay? And if we divide that by M2, now we could divide it by M1, but either way we'd be left with one mass that would be got rid of, okay? Just easier to get rid of M2. So GM1 over R squared, okay? Then we sub in the values that we get for Earth. Now there's the sun here, there's Earth, and I'm sure you could do this for the moon or whatever you might want to do, okay? So, remembering that the G is just a gravitational constant of 6.67 times 10 to the minus 11 Newton meters per kilogram, etc. And then you would sub in the mass of any planet you want to work out and the radius of any planet you want to work out. Obviously, they have to be of the same planet. Alright? And you could come up with your own planet. Well, if this was the size of the planet, what would the field strength be? And you could plot a graph and come up with your own equation of the constant, which obviously should have G. Anyway, so the mass of Earth in kilograms is 5.98 times 10 to the 24. Okay, so obviously that's heavily rounded kilograms. And the radius, again heavily rounded, 6.37 times 10 to the 6. But remember, we have to square that number as we're told at the bottom. Okay, and if you put that all into your calculator directly as that, a G comes out to be 9.83 something, which is very close to 9.81. Obviously I did that calculation in my head there. I've not done it before. Okay, and it's not in this book, but that's the page I'm on, and all the page says is a couple of numbers, so I'm not cheated. Or maybe I'm just a genius, okay? Anyway, so it's G's 9.83, and obviously that's standard values of G, which you can find by putting the units together. Anyway, that's Newton meters squared per kilogram, okay, and you times it by a kilogram, which cancels out the kilogram, okay, so on the top it becomes Newton meter squared, and then obviously you've got obviously the radius in meters, so it's meters squared, so therefore it's just newtons, okay, or newtons per kilogram, sorry. Anyway, it doesn't really matter, because I just think that's the value that you would be given. Okay, I know I said this is the true value that we know it to be, but that is, you know, clever people have worked out. We've worked 9.83, and to us it doesn't really matter that much, okay? So it is close enough, and the only reason that it's not 9.81, and the only reason, as I said, there's one reason, the only reason, is the fact that I've used rounding errors. So if you go on the internet, I'm sure you can get a much more accurate value for the radius and the mass of Earth, or you could just get a tape measure out and measure it around. This, you know, pretty long tape measure. Probably have to go to Halfords or whatever. And Everest paid me 10 quid to say that. Anyway, they haven't, unfortunately. Anyway, so as I said, that's how you would work out G. So it's very nice. You can work out the gravitational field strength and the surface. Now this is, remember, this is on the surface of the moon. This R, which we said ideally when we were looking at Newton's law of gravitation, we said R is the distance between two objects. But because we're not considering another object, well, technically you could say, well, you're a person measuring the field strength, so technically you're a mass, but it's so it's so negligible, it's not really going to affect it, okay? And you're not measuring a field strength, you're not measuring the attraction between you and this planet, you're measuring the gravitational field strength, G, okay? So we don't have to take into account the other mass that's measuring it, whatever, okay? So that's how you'd work G out. Anyway, what we're going to do now is just going to, obviously that was a nice little side thing, and you might get asked to calculate the gravitational field strength, you know, of the moon, or prove Earth to be approximately 9.81, and that's the kind of thing you would do in the exam. So they could ask that. It is interesting, and definitely they could ask that in a question. But what we've said here, sorry, I take rubber. We've said that G is equal to GM1 over R squared. But we've also got here G is equal to the negative of the potential gradient. In other words, it's equal to negative V over R. What we're going to, that V is the gravitational potential. Okay, so we're going to work out the gravitational, well, I'm going to come up with another formula to show that we can work out the gravitational potential at any point along the Earth, going away from the Earth. Because we said we had equipotentials, but we might want to work out, well, if we're at 700 meters, what is that field strength at 700 meters, or what is a field strength at 700,000 miles or 200,000 miles? You get the idea. Okay, that's a very crap drawing, but what we do is obviously this is equal to g, and so is that. So we put the two g values equal to each other. So in other words, gm1 over r squared is equal to negative v over r, and we want the gravitational potential at a certain point. Well, quite clearly, it's just a case of simplifying these two equations together. So we times both sides by r, so we get negative v is equal to negative the gravitational potential is equal to gm1 over r. Because obviously when you times something 1 over r squared by r, you're just left with 1 over r. Okay, so in other words, gm1 over r. But that's equal to negative v, so quite clearly therefore v is equal to negative gm1 over r. Okay, so that's gravitational potential at any point that's the distance from the centre of Earth. Now, one key thing here, with these kind of questions, r, now that's the distance from the centre of Earth, not to the surface, okay? So if you're 700 miles away from Earth, which is nothing, as I said, but I'm just trying to keep it in relatively small distances, you've still got to add on the distance to the centre of Earth as well, because, as I said, gravity acts at the centre of mass kind of thing. So, centre of gravity is just the centre of mass times by 9.81, okay, which is obviously what I've just worked out over there, right? But as I said, if you're working out the gravitational potential at some point away from Earth, you've still got to take into account not only the distance that there is to the surface, but we've also got to add in the distance to the centre of Earth, okay? Alright, so hopefully that makes a little bit of sense. There's nothing too difficult about that. So is that it? Gravitational potential? Yeah, that's the end of this, the gravitational potential videos and of gravitation. We're going to go and look at a bit of electric fields next, okay? Which is, there's nothing too difficult, but I'll just give you a bit of a heads up if you're obviously still listening, which you clearly are if you've listened to this. I'll just be explaining a bit about what electric field strength is, and then I'll be going on to similarities and differences between electric field strength and what we've been looking at today of gravitational fields. Okay, they are very similar, but there's some key differences that I'll be brushing over. Okay, and I'll probably do a video with a table that states the similarities and differences between the two. Okay, so thanks for watching. Hopefully it's not been too boring, and we'll see you in the next video.